Am I on? It looks like I'm on. Welcome everyone. Thank you for joining me. I know it's been kind of tricky to get here. I got stuck in a traffic jam. And I'll start with a bit of an apology. You're not gonna make lunch on time. No way. I mean, I'm already delayed, but in exchange, besides my 60 slides, I'll also show you 2 demos. So, first off, let's start with a quick story. I'm Kostya working at Elastic, and a while ago, Breda, my colleague, which is pictured there, wanted to figure out what's the happiest team in Elastic. So this was, in hindsight, really an excuse for her to play around with machine learning, which she happens to have a PhD in Elasticsearch. So Breda and myself ended up working on this POC, where we were trying to sort of eat our own dog food, figure out how far we can stretch things. And along the way, we learned several things, some of which I'd like to share with you in this session. Mainly on how you can improve your machine learning pipeline by using data structures or algorithms from information retrieval. So if you're doing text processing, in particular things like analysis or featureization, this might be of interest. Now, everything that I'll show here is based on this POC, so it's kind of experimental. The code is there in the open source, you can try it out, but there's no real guarantees. It doesn't mean necessarily it's a product. It's just something that we have worked on. I also like to touch on something that's been quite prevalent in machine learning, but is not widely talked about, and that is technical debt. Google published a nice paper a while ago called Machine Learning, the High Interest Credit Card of Technical Debt. As you can see, quite expressive, quite concise, in which they argue that when you're doing machine learning, a significant amount of time and resources are spent on services auxiliary to machine learning, not ML itself. In fact, in this picture there, the small black box in the middle, that's machine learning. Everything else are supported, incidental complexity that you have to carry around. So here, today, I'd like to talk on how potentially can eliminate some of that complexity, in particular when it comes to analysis and feature extraction. So when Brenda and myself ended up on this challenge, we first had to figure out, well, how can we discover what's the happiest team? Now, in this case, luckily enough, Elastic is a distributed company. We are working around 23 countries, so a lot of the communication happens in written form, whether it's email, issues, comments, or instant messaging. So this proved actually to be a nice candidate because typically when people are talking on instant messaging, first of all, the messages are short. Second, they tend to be less formal and they're public. So there's no worry about privacy issues here. So we basically took our HipChat data, which was the service that we were using back then, and then started doing data crunching on it. Now, because most of the lines, most of the text was fairly short, less than 200 characters, typically around 100, rather than building our own model, rather than training ourselves, we used Sentiment 140, which is a project started several years ago by several students at Stanford, where they did sentiment analysis on top of Twitter. And they were nice enough to publish that model, so we basically took that out, adjusted a bit, and used it. And then we published the results in Kibana, which is a web UI. So by using Elasticsearch, and you'll see why that's relevant, and Lucene, we put the data in, then we took the model, worked through MLlib to do a bit of adjustment, and then we ended up with the actual model that we use to do this classification, and you see at the end what we got out of it. Now, as you know, whether using machine learning or not, data is critical, whether it's about creating the model or whether it's just working with it. So here is an example from Spark, since we're at Spark Summit, on how text would look like, right? This is an algorithm word to vec, it's a transformer, and this is what the input looks like. Now, if you look for this source throughout the internet, you're not going to find it like this. This is ideal. What you're going to find is like this. This is actually the same text available at Wikipedia. And you notice that it contains something extra, some metadata, in this case, HTML tags used for rendering. So typically when you work with data, you'll find out that you not get the raw source that you're interested in, but something else alongside with it, so you have to differentiate with that. Moreover, especially when you're dealing with human-generated data, well, you have exceptions that end up being the rule. You have shortcuts because people don't like text. So you have things like LOL, OMW. You have mistakes, sometimes on purpose, sometimes not, and letters that keep repeating themselves over and over again because, well, the author was really enthusiastic and wanted to, convey something. this ends up having a critical impact on the way you deal with the data, and in this case, on doing classification, because, well, what do I do with things? Do I discard them, or do I match them? If I do I do it correctly? In fact, the folks behind Cinnamon 140 mentioned this quite at length in their paper that they published. And to state the obvious, the majority of people in the world do not use English. In fact, their languages are significantly different, both semantically, syntactically, and guess what, encoding-wise. So what can you do when you have such a breadth of problem when you're just starting to work with the data? Well, I would argue that one obvious solution would be Apache Lucene. First of all, it's open source and is widely regarded as the most advanced library out there when it comes to text processing. It's really a state-of-the-art engineering, and it's been around for a while, so it's widely used. You have various tools at your disposal, but for the most part, you have character filters, so you can just look at the data and just disregard the noise. And then based on your language, you have different analyzers that basically break down the text into tokens. So you know where they occurred, what position, how, and their length. And then you can do additional filtering on top of that. So while Lucene is great and has support for a variety of languages, pretty much every language out there, it's a library, which means you have to write some code. Now, there's nothing wrong with it. I'm an engineer, I'm a coder myself, so you just look at it, you start coding. If you're an advanced user, if you're doing some kind of analysis, if you're doing NLP, that's what you should be doing. But if you're just a user that has a body of text, whether it's English or Spanish or Chinese, you name it, and you just want to break it down, you don't necessarily want to write this code because that's code you have to maintain, you have to understand, and guess what? Zero code means zero bugs. So you're going to introduce some bugs as well. So maybe, just maybe, there is a way in which you can achieve this and play around with doing text analysis without necessarily having to write some code. So let's take a look at how that looks like. Just to give you guys a glimpse of how you can use this type of text analysis, which is quite useful. I'm using Windows because I like challenges, let's put it this way. And what you see here is just a web UI, right? It's JSON. If you're not familiar with it, doesn't matter. I'm just doing some HTTP calls. So you can do curl, but you'll see this is just a client for Elasticsearch. You'll see later on why this makes sense. So one way of interacting with Lucene, for example, is to start and throwing text at it and see what we can do. Very easy, right? I'm not writing any code whatsoever. So I have this basic text, Mary get a little lamb. So I'm just going to analyze it, which basically means I'm going to take the standard analyzer in Lucene, which is based on English or English-like languages, and it's going to do a tokenization. These are sort of standard defaults. And you can see that I get back a number of tokens. In this case, they're alphanumeric, that basically break down the text. In this case, would be letters. Now, if I take the text that I just mentioned from Wikipedia, I get the same thing, but obviously you can tell that I have the A and the href and HTTP. Basically, the HTML tags are in there. This is something incidental to my actual code. This is something that is relevant for the HTML render, but not for me. So one interesting thing that you get out of the box is the fact that you have a bunch of tokenizers, and in particular filters and character filters. What this allows you to do is basically disregard a body of text based on certain semantics. And one of them is called, guess what, HTML strip, which what we'll do is look at it, understand the HTML tags, which are quite popular, figure out the beginning, the end, and basically just exclude them. So the same text I get, it was mathematics in the, right? The whole links here was basically removed by the char filter itself. Now, if you look in Wikipedia, which tends to be the ultimate dictionary of knowledge, this is the actual Wikipedia website and the documents in it, and you can see how it looks like. This is the raw code, the raw text that you have in there, which is full of HTML tags in order to be rendered. So one thing that I can do here, and this is quite powerful, is say, you know what, the data that I have, it's scrambled. But I don't want to process it right before because maybe I'm interested in the links as well. Maybe I'm interested in these anchors. So what I can do is actually index the text as is, and as I'm looking at it, actually do the transformation on the fly. So what I'm doing here is literally saying, this is the actual body of text that I'm looking at, but I'm interested in field text, in this case this one, and I'm interested in getting it back analyzed through HTML. So I can actually get this content without necessarily doing the transformation before saving it. This gives me a lot of flexibility in trying to see the same data from different points of view, removing the noise and basically applying a filter, focusing. Now, for those of you that understand Chinese, I personally do not, you know that it's significantly different than English. So what I've done here is literally take a body of text and just run it through the standard analyzer. Now, if you put the same text here, right, first of all, the tokens are not alphanumeric anymore, are ideographic. Basically looks like a drawing. And you can see that each of them is taken as a token. Now, if you add that into Google Translate, it will do something like this. Luke Lost Purcell suspected terrorist attack committed heritage introduction exposure. So it is concerning because it mentioned terrorists, but everything else does not make sense. Who is this entity, Luke Lost Purcell? What does it mean? Now, this is the thing with languages. Languages are different, are not just the representation is not only different, but structurally, the way the relationship between tokens is designed is different. So if you apply the same text through what is called smart Chinese analyzer, you get different tokens. Basically, in this case, the input is not garbage anymore, but actually it does make sense. Now, notice that we don't have ideographics anymore, but actually we have words. And these words actually translate to, again, through Google Translate, Brussels Testament exposure terrorist attack suspects. Unfortunately, it's still about terrorists, but actually now it makes sense, right? Because in Chinese, actually, you don't just take letters one or the characters one by one, but actually you group them, and based on that, you end up with different semantic, different context. Quite different, for example, from English. Now, coming back to our amazing and the whole analysis on Twitter, where basically people are not necessarily writing English, you have a lot of write recurrences, as I mentioned. So here we have the Sentiment 140 model, which was indexed. And what I'm basically saying here is, give me all the terms that you've indexed from amazing, they are ordered alphabetically, and give me the first 100 terms. So I'm looking at it, and they look like this. Now, the interesting thing that I can do here is I can just define my O analyzer. Now, obviously, I can write code for it, but luckily enough, out of the box, I can just use regular expression, for example, to say, if you encounter within a body of text, within a word, a letter that keeps repeating itself, just remove and just use it once. So what I end up doing, I'm just defining this one, right? This is a live demo, folks, so they're bound to be errors. What I'm doing here is basically saying, define this analyzer that I just created. It's a custom analyzer. I'm just baptizing collapse, repeat letters, filters. And then if I'm applying it on a body of text like the new Brave Citizens songs are amazing, I get something that actually makes sense, which is a normalized form, a form that is actually the core of it, where I'm just removing this emphasis on it. Potentially, I can influence that for scoring, but in terms of looking at the word, I can actually find its root sentence. Now, the interesting bit here, and this again applies in looking at the whole chain, is not only you have to look at the source of the data, but actually have to look at the queries themselves. So in my case, the source contains amazing with the variety of A and G's uppercase. But when I'm searching for things, maybe I'm going to search a document which by itself, a query by itself is incorrect. For example, here, I'm doing a query, I'm saying, find me all the documents that are amazing, right? But in this case, I have a different number of A and G's. So one thing that happens, and that applies to every information retrieval engine, is apply the filtering both on the data that you're looking for, but also on the query. Because you want to end up with the same normalized form so you can actually find the same matches. So in this case, amazing does match my document as well. So this was just a quick glimpse of, perfect. Just a minor bit, there we go. So what you saw there was basically using Lucene through a REST endpoint, in this case for Elasticsearch. I just ended up throwing some text at Elasticsearch and leveraging the Lucene libraries underneath, saying, I want to use a standard analyzer, I want you to bring this text for me and potentially process it for you. So how many of you here are familiar with Elasticsearch, by the way? Okay, quite a bunch. So this introduction is going to be very short indeed. It's a scalable real-time search analytics engine. You've seen the REST API. It's open source, provided on GitHub. And you pretty much have used it through the various websites that are using Elasticsearch. For example, Wikipedia uses Elasticsearch, so whenever you look for an article, you're doing what is called unstructured search, or basically you're doing a query, getting some answers back. On Stack Overflow, you get the answers being sorted on relevance, so you actually have multiple answers, but they're based on what's most interesting to you. This is called scoring, and this applies also if you have small data or what is called big data, which is an interesting problem because you're sorting a large number of data before handing it, returning it quite fast. GitHub is also a somewhat well-known user of Elasticsearch. You can see things like highlighting, where you're searching for a project. This is enrichment, where you figure out what occurred and where, in what context. And also a good exposure of the analytics parts. So what happens here is you're running a query, getting the answers, and as the answers come in, they're being broken down per type. So you have repositories, code, issues, users. And also the repositories are further broken down into the language, like JavaScript, Java, and so on and so forth. And none of this is pre-computed. Actually, you run a query, get the answers, and as the answers stream, they're being broken down based on this criteria. Now, all these websites have a large amount of data. For example, GitHub has terabytes of data. And there is a lot of write activity. You have issues, you have pull requests, you have comments. People submit them, and then they immediately become available when you search for it. So this is what we mean by real time. And as you can imagine, the scale is pretty large. This is what we mean by scalable. But Elasticsearch doesn't just work with human-generated data. It also works with machine-generated data. And a favorite use case of mine is the Mars rover from NASA. Now, what does it have to do with machine learning? Well, if you look for documentation, you're not going to find an entry chapter where it says, this is how you use Elasticsearch with machine learning. But if you look at information retrieval, and if you start working with Elasticsearch or with text analysis when you do machine learning, you find out a lot of similarities. For example, when you're searching for data and information retrieval, you end up with scoring algorithms like term frequency, inverse document frequency, BM25, which is the next generation scoring algorithm. And all of that are based on tokenization and term analysis, which make some very nice feature algorithms. We also provide graph analysis, which is based on finding the relationship between the various terms. So not only that this text is broken down in tokens, but what's the relationship, which is kind of interesting when you're looking at things like NLP. And also in terms of aggregation, there are a lot of operations that, again, are excellent for understanding the data. Things like significant terms, which, again, is based on concurrence of terms, also has its own chi-square algorithm, if you're into that, Pearson correlation, and regression as well. Now, I'm not saying Elasticsearch should replace machine learning. That's not going to happen simply because Elasticsearch is about fast data. So we're thinking milliseconds. Seconds become slow. 5 seconds is borderline slow. 10 seconds is way too slow. So machine learning is the opposite of that, right? It's about looking for a lot of models, doing a lot of data crunching. However, what if you can enrich your machine model, your pipeline, by relying on this feature? Because then you potentially get some benefits. And you'll see why that is. So when Brent and I myself ended up on this journey, we figured out that what we want to do from Elasticsearch is not return the documents. Hey, you run this query, you get these documents, these matches, but actually trying to find the metadata behind it. How did you find these things? What's the relevance? How did you end up devising that particular score? So it's about the internal structure, about vectors and things like term frequency. So as a quick side note, if you want to use Elasticsearch from Spark, there is a project out there called Elasticsearch Hadoop, led by yours truly. Does integration between the variety of projects in Hadoop and Spark. And Elasticsearch, in particular, Spark actually has the richest integration out there. Supports Java, Scala, works with Scala 2, 10, 2.11. Available as Spark package, supports Spark 1.0, 1.6. And for the most part, it means you don't have to get out of your Spark environment. Actually, for the most part, everything is just one-liner. So you can take any RDD or data set. We're working now on Spark 2.0 support and just save it to Elasticsearch, which means it literally is indexed. Or you can read data from Elasticsearch, which basically means you're running a query and you get the results back for the matches. If you're using a data frame, we support that as well. So not only you get access to a structure view on top of Elasticsearch, but any operation that you do on the data frame gets pushed down. And I would argue the Spark SQL support in Elasticsearch Hadoop is probably one of the most advanced there because it supports all the filters within Spark itself, which means pretty much any operation that you make outside joins is actually pushed down. What that means is when you do, for example, this case here, looking for a category and year, you don't have to load the data in Spark and then Spark does the filtering, but actually Elasticsearch automatically at runtime is going to generate the query DSL, does the filtering in Elasticsearch, and only return the results, which is highly efficient. Now, one thing to mention is everything in Elasticsearch Hadoop is parallelized. So as your cluster it grows, as your Elasticsearch cluster goes, as your Spark cluster goes, so does the parallelism between the two. So let's put all the pieces together. Now, this is your typical pipeline for text processing. And again, this is taken from the Spark documentation. Right? So I have my raw text data there. I'm doing a transformation on it. I'm doing the tokenization. I end up with the words. I'm doing a further tokenization. In this case, I want to find the features. I'm applying term frequency. I end up with the features. And then I end up with the logistic regression. Right? So there are several things here that stand out. First off, that box there in red, that's the actual ML code. Everything around it are supported services. So this is literally a trivial example where I'm doing a lot of work, basically 66% of it, of taking the data, munging, in order to actually get down to my ML pipeline, to my logistic regression. So clearly there is something there that it could do. Now if you look at the code, this is what it looks like. I take my data set, and I'm putting through the pipeline, and then I'm getting my actual model that I'm trying to fit. So let's focus on this one. Now, the tokenizer here is a white space tokenizer. It works for English. If you have anything special, it's going to break down. So let's do something here. So one thing that we've done is we extended the ES Hadoop connector, the Spark integration, to basically provide an in-place replacement that does everything that I've just showed. Basically leverages the whole Lucene infrastructure where you can have an Elasticsearch analyzer that understands Spanish, Chinese, English, all these goodies that you've seen, and it's exactly the same replacement. The same input, you get the same output. So now you can throw a lot of languages at it without having to worry about it. Now, what about the hashing function here? Now, as some of you might know, this is an approximation. Because you're doing machine learning and you don't really want to build a whole model, what you're doing is you're saying, well, I expect up to, as you can see there, up to 1,000 terms, which means I'm reading a lot of text, and I'm doing an approximation. I think they're going to be around 1,000. If they are more than that, I have a problem. If they are less than that, I have a problem, which means suddenly my model breaks down. And this is a problem because suddenly you have words that have no relationship with themselves that get hashed to the same partition. So that's a problem. Not to mention that due to the way how Spark works, where each worker has a slice of data, its own view of the data, which means one worker is going to see some terms, the other one is going to see the other terms, but still their hashes might be the same. So maybe we can do something there, but rather than just say, let's use a term frequency or BM25 for Elasticsearch, there is a different issue here. And first off, you take all this data, you throw it Elasticsearch into the tokenization, and get it back, right? Forget that this is Elasticsearch here. I'll assume there is a different system, right? Then I have the words. So pretty much it's the same copy of the data, but broken down into words. I'm throwing it again in order to do the hashing, and I get back the feature vectors. There's a lot of data that goes around and around here. If I want to change my model, if I want to change my logistic regression just a tiny bit, if I want to add a new stage, I have to redo the whole thing over and over again. The data is the same, and I do the same tokenization. I do the same hashing over and over again. So maybe there is something that we can improve here. So why not, bear with me, this is a crazy idea, why not just do this work once so I can take my body of text, I know it's English, I've done some analysis on it, I've figured out a way to properly tokenize it, and now I'm happy with the results. So I'm just going to do it once, which basically, with the connector says, take this data, save it to Elasticsearch, which basically means index it, and that's it. You're done. Now what about the hashing? And this is a new API that we added to Elasticsearch and this is Scala with JSON, but you can pretty much understand. Elasticsearch, because indexed all the data, it knows a lot of things. It knows how many terms there are, how many in documents it appears. It has a lot of information because this is what it excels at finding references, finding information. So we can tell Elasticsearch, you know what, I'm going to create a spec. I'm interested in field text, which is of type string, and give me all the occurrences that appear in the index more than 2,000 times, and return that information to me as a sparse vector. And this is cheap. This is cheap because in Elasticsearch, we just tell it, give me that inside information that you have. I'm not interested in the documents. Give me the information behind the documents. So I can just use the spec right through the API. I'm just declaring it. And then I'm saying, run this query on ML data, basically run this script. Give me not the documents, but actually give me the spec that I just defined. Give me all the terms that appear on field text more than 2,000 times. And what do I get back? I get an RDD that contains, because in this case I'm using the Sentiment 140, or for example the movie reviews, the label, whether it's negative or positive, what was the review there, and the associated vector with it. I can transform, I can say negative is 0, positive is 1, potentially neutral is 0.5, transform the actual vector into the vector format in Spark, and end up with a data frame that I could just feed to my ML pipeline, which now looks like this. Give me not the raw data, but actually give me directly the vectors, feed that to the logistic regression, and end up with a model. So I have the same pipeline here, but actually what I'm doing is doing the tokenization once per data set, doing the hashing per data set, and then I can just adjust my logistic regression. I can add whatever stages I want, that work there is done. I want to change the data, no problem. I can add more data to it, that data doesn't go away. Right? So not only I've improved the speed, but actually I've also reduced the complexity. Now, what if I want to adjust the model? Well, it's pretty trivial. I'm going to define a different spec. In this case, I'm saying, don't give me all the terms, but actually here is a list of terms that I'm giving to you, and tell me their terms frequency. And again, return everything to me as a sparse vector. So coming back to our question, I know there is lunch there, but trust me, you're going to see some very nice graphs here. Eye candy, food for the soul. So this is what the movie reviews API looks like. I have the data from HipChat. You're going to see it, but because I like my job, I'm not going to actually expose all of it, because you never know what happens when the demo gods are not pleased. So I'm just going to show you the demo reviews, the movie reviews data set. So again, what I'm saying here is give me all the terms, pick the one that have at least 2,000 occurrences, and give me 100 of them. And this is what it looks like, right? These are the terms. So what I'm saying here is, you know what? I'm interested on this particular data set, on this particular index, on the field text. But you know what? Look at the number of terms. I'm going to give you 3, good, bad, ugly, and give me the term frequency. So I'm just defining this PEC, right, which is, as you can see, very quick. And now I'm doing a search. So this is an interesting thing here. I can take a look at all the documents, or I can just find the document that matches a certain query. The restaurant within 2 kilometers, movies that have positive reviews, movies that have a director, Quentin Tarantino. It doesn't really matter, right? Except that rather than taking the documents that match a query, I get their metadata, their internal information. So in this particular case, I'm just going to do a straight movie review. I'm saying, give me all the documents. I have around 52K of them. And what I get back is this information, right? So I gave 3 terms, right? So I have a vector which has 3 indices, starts from 0, so I have 0, 1, 2. So in this case, index number 1, namely bad, has value appears once, right? It's a sparse vector, so everything else doesn't appear. Once, in this case, in this document, appears 3 times. 0 and 1, so good and bad. The first one appears once, the first one appears 3 times, so on and so forth, right? I can even have empty indices, for example, for documents that do not have this occurrence. So now, based on scoring and matching, I can actually get the terms vectors, which is great because it means I can actually feed this information directly into the data, to the ML pipeline without having to redo this work over and over again. So we use the same analogy when we index our HipChat data to figure out the sentiment analysis. And hopefully everything looks like this is water cooled, so everything should be okay. This is what type of messages we have here, when it occurred, the author, and the text. So something will be readable, something about performance on their laptops, whatever. So let's answer sort of the question that we ended up with. Okay, what's the happiest team at Elastic? So we ended up in the data that we had for 5 years with this 5 rooms. So basically broken down the data on 2 axes. One is per time range, so give me all the data within 5 years, and also bucketed per room. And once you have that, do the analysis, basically. Find out the matching. Is this room, are the messages that find in this range, are they positive or negative? Are they happy or not? So we figure out that, well, marketing is the happiest. This is our basically top 5. We have more rooms than 5. Marketing is the most happiest one. They ended up with, well, Kibana is not very happy. Well, it is 55, I guess. Then we ended up with support. Interestingly enough, dev room, and then Logstash seems to be trailing behind. Now, again, I can easily change this data, and if you look back here, if I'm moving from 5 years to 2 years, you noted that things do change because, well, we have another room, water-cooled, that was added, that seems to be happy. Marketing improved a bit, and Kibana and support still are not happy. Well, I guess you can imagine why. One probably is because of rounded corners and boxes. The other one is, well, because of support. So, what happens behind the scene, just to give you a glimpse of what this looks like. This is the actual bucketing that happens. This is sort of what the request looks like. I'm just saying, do this query. I can find any query whatsoever. And then do a filtering plus aggregation, basically break down the data into various terms. And then give me, this is what the response looks like, right? Which is rendered here. As you can expect, is basically tables and numbers, right? This is what the table representation will look like. So 1 is happy, 0 not happy. 1 is happy, and so on and so forth. So this is sort of the last slide. If you have any questions, I'd be more than happy to answer them. Currently, what we have is exposing sort of the obvious information that we have in Elasticsearch, and that is currently the dictionary, the term vectors, and the analysis that is performed on it. Whereas the term frequency, inverse document frequency is useful, but not so much. But also, we're looking at BM25. Now, this works with both data which sits outside Elasticsearch, so data that you can throw at Elasticsearch to do the analysis, but the whole analytics, the whole aggregation works so much better if the data is in Elasticsearch, simply because the data is local, it doesn't have to move across, it's already partitioned. There are a lot of things that work behind the scene to make that information happen. This is what I basically did in my demo. And also, everything here is bound to a query, which means you can take your data set, put it there, and then run different queries to figure out a slice of your data and then train based on that particular data. You don't have to just partition it. You can just import it and then run different queries, which is gives you quite a nice feedback loop. Now, in terms of other things that we're looking at, I just mentioned text classification, but there's also things like numeric support. Things here change differently, and there are several things in terms of performance that we can do. And also looking at importing and exporting. You have a model. Maybe you can just import it in Elasticsearch and do this classification, or you can put it into Elasticsearch to do the enrichment and then export it back to Spark. And this is an area which we're looking at it. In Spark 1.x, it was PMML, and now there's a different persistence, so we're looking and figuring out exactly how you can enrich that model, particularly because the model also entails a whole bunch of transformers behind the scene. So if you have any feedback, we're highly interested in that. One thing that I've not mentioned, and I'm just going to mention now, if you're looking at the whole thing that I've did here, it's the demos, you can find it on GitHub as a gist. There's a short link there that you can just use, so you can try it yourself, no worries whatsoever. And also, you have on GitHub the source code for both the extension to Elasticsearch Spark and also the extension to Elasticsearch to have this new API to play around with the vectors. If you have any feedback, that's where you find that online. I'm here as well. Thank you so much.